There we go. Okay, we are recording now. And I've got a question for you. I brought a little toy for you that you might remember from way back when.
Toy.
This is a little Duplo Lego piece.
Duplo?
There we go.
Duplo.
Or is it? This is
Bye.
actually
Legos.
not. Okay, guys, shut up or I'm going to mute you. This is not a Diga situation. Okay, settle down. Okay, so this is actually not a piece of Lego or Duplo. This is actually a proton. Okay, just pretend. Okay. It's a proton, and if it's a proton, okay, and we can label that to make sure we know that. We can write a P on there. Back with a marker. Marker. Yeah. There we go. There we go. We're gonna have a proton here. Okay. But then if that's a proton, kind of can already guess what maybe this is. It's the same size, just about, but it's a little bit different. It's a neutron. Very good. So this is a neutron. Yeah, you guys are brilliant. Smart people in 9D. Always knew it. Okay, so we've got a proton and a neutron. That's cool. We're gonna stick those together and do a little bit more of this. And tell me what this is now that we've put 4 of these together like
Nucleus.
It's that nucleus, exactly. Does anybody know what nucleus this is? No. What nucleus has 2 protons and 2 neutrons?
ERB.
Nitrogen. No, hydrogen only has 1.
Yeah.
Is it helium?
It is helium. You guys are brilliant. Very, very good. Okay, and that's going to give us a good opportunity to talk about specifically these 2 numbers. You've seen that for helium and for other elements in chemistry class before, I'm guessing. Let's talk about those numbers. Now, your chemistry teachers told you what those numbers mean.
Yes.
Okay? Yes.
Are we supposed to write this down?
Oh, I love that. That's cool. That's a good question. I get that question during live class too. The general guideline that I always use is if the teacher's writing it on the board, it's worthwhile writing down for you guys. But it's your call because it is recorded. You might just decide not to. You could always go back and write it down. But it's probably a good idea to keep notes. So this bottom number, your chemistry teacher told you what that number means, and what name did they give that thing?
Atomic number.
Good job.
Hello.
Okay, and they also gave this thing up here a name. What's the name they gave this number up here?
Atomic mass.
Atomic mass. You guys are awesome at chemistry. You guys are awesome at chemistry. But guess what?
Thank you.
I'm going to let you guys know that both those terms in this unit in physics are going to be wrong.
Oh my god.
Oh my god. So that's not what that is at all. And that's not what that is either.
Coffee?
And let's come back to our little thingamajigger, and this is the nucleus we're talking about, because what we're doing here is nuclear physics.
Whoa.
Yeah, I know, it's crazy. So we're doing nuclear physics, and we're doing nuclear physics.
Crazy.
Why does nobody have their face on?
My dream
Because
job.
this is on YouTube.
Yeah, please keep your camera off if you come new on, and stick with that, please. Okay, so we have here a good example of a nucleus, because nuclear physics deals with nuclei. Hello, that makes sense. Okay, so let's take a look how we can interpret those 2 numbers, 2 and 4, based on knowing that this is supposed to describe this thing. Okay, so let's see what we have here with the 2. The 2 we have down here, okay, the 2 is actually a synonym in certain ways for helium, because it refers to the fact that this nucleus has 2 whats?
Protons.
Protons, exactly.
Neutrons.
Because if you look at it, not the number of neutrons, that's not the key thing. We could take one of these neutrons off, we'd still have helium, but it would be helium-3. This is an isotope of helium. Okay, that's
My
called
turn.
helium-3. So helium-4, this picture we have over here, we can think of having two.
I don't know.
Mode.
Calm down.
Let's
Is
show up.
Mr.
Let's show
Westman
up.
also in school? Because the lag is real.
I
So
don't see
this
Mr.
is
Blessman.
Mr.
And
Lesson.
yes, the lag real.
It's showing up okay. It's a little small.
It's very small.
I
I'll make
see
it
it. I see it.
I'll get you a
I
little
see
closer
it.
here, and
Yeah,
I'll draw
because
the
you're
second
small,
one a
Sam.
little bit bigger
Shut
there.
up.
Okay. So we could also talk about helium-3.
I'm 6'2".
Stop talking, please. This is a class. Stop chatting. So otherwise, I'm going to have to block you. So we're going to draw this one a little bit over here, a little bit bigger to make sure you can actually see it better. I think that's showing up better.
Very colorful.
Thank you very much. I've been working on that. So we've got 2 protons still. And then we have 1 neutron. This is called helium-3. So both of these are helium, actually. And the idea that these are different, if these numbers are different.
Mr. Blessman, could you zoom out a little bit because I can't see the complete board?
Yep.
Aaron, you can move the thing.
Oh, it's actually all showing up. So I think it's you.
Yep.
Oh.
You
Yeah,
can
it
move
is you.
the
Okay.
thing
So
to the right.
isotopes of helium have different numbers of neutrons. You see that? But otherwise, they're the same. So based on that, we're going to take a new name to these two things, because this is really the number of protons, agreed? Not really the atomic number. And we're going to go a little further, and we're actually going to call this number, go with green here. We're going to call this the charge number.
Oh my.
Okay, because the charge is +2, +2. Now we don't need to see the plus there, but it is a +2. Okay, so the other number, if you look at that number, that's really the number of how many particles we have all together in the nucleus. Here it's 4, here's 3. That's why that's 3 and that's 4. So that number is really the total number of protons and neutrons together in the nucleus. Protons, neutrons in the nucleus, we will take those together and call them nucleons. That's a portmanteau. You guys know what a portmanteau is?
No.
A word that combines 2 words together and makes it into a new word, taking the front of one word, the back of the other word, and stick them together. Auf Deutsch Kofferwort. You might have heard that before. I'm not sure. But anywho, this number. Oh, we're going to go with green. This number we are going to call the nucleon number.
Interesting.
Interesting. And there's a purpose for that. And the purpose will make. Hi, Macy. Can you stay off, please? Your video? Thank you. Okay. So
Sorry, I didn't mean to do that. I was just
all
checking.
cool. We're all good. It's all good. So, so the nucleon number and the charge number will be important.
Okay.
Bless you.
Gesundheit. Hope you used your elbow.
Yeah, don't you send one.
So, okay, cool. So that's the basic idea. Everybody else good so far?
Yep.
Nothing too technical? Okay, now comes the hard part. So the reason I had these with me was because I wanted to show you something, and I wanted to show something to you that's a little bit strange. I have here a little kitchen scale. I use that for baking. Isn't that fun? So we're gonna do yeah, I think so too. We're gonna
That's
do
insane.
We're gonna do a pretend weighing session with our scale. Can you guys see that? Not really.
Yeah.
Yes.
Yeah.
Here it is. There's a screen. See this screen? Okay, I'm going to pretend. I'm not going to actually show you. So here's what we're going to do. I'm going to take this guy here, this one, the proton. I'm going to weigh it. Okay. And then I'm going to take another proton, and I'm going to weigh it. I'm going to take a neutron. I'm going to weigh it. I'm going to take another neutron. I'm going to weigh it. All good?
Actual-
Makes sense? Actual neutrons, but because those are so small, I really don't want to use those because I think they're very hard to understand, the numbers, right? Because they're like all like 10 to the minus 27 and all that crap. So that's hard to get. I'm going to actually write the masses on here that I measured.
Wow.
The mass of the proton. I'm going to pretend the mass of the proton is
It's a high-end device.
20 grams. I wrote that right on the scale. Got that? Okay. I'm going to say the mass of the neutron is also 20 grams. Okay. So not surprisingly, when I take my 4 of these and I stick it on here, measure the mass. What's the mass I measure when I measure the 4 particles at the same time?
80.
80 grams. You guys are so smart. Okay.
Hi, Philip.
Thank
Write that
you.
on here. So
Hey.
Luisa just spent 800 Euro.
So here's the result. We found that the mass of 2 protons and 2 neutrons together is 80 grams. Everybody cool with that?
Yes.
No surprise. Okay, now watch this. Famous last words of skateboarders everywhere. We're going to take those 4 things and we're going to combine them into helium because that's what that is, right? That's a helium nucleus. We just talked about that. So now I put those together and I've got a helium nucleus. See that? There's my helium nucleus. Oh, now my scale actually came on. Whatever. Okay, so you get the idea? And now I'm going to remeasure the mass of the helium nucleus. Got it?
Yeah.
You guys tell me what the mass of the helium nucleus is.
80 grams.
80 grams.
80 grams. I feel like 80 grams is wrong.
80 grams.
80 grams is wrong.
It's gonna be
90
less.
grams.
90 grams is
40.
also wrong.
100
40
grams.
grams?
You guys
I
are
don't
just guessing.
understand. What
I'm
is
going to
the
get to it
question
just a
again?
second.
I say 100 grams.
I'd say
I
less.
say 40.
I measured it,
it.
and it's 70 grams.
What is the
Whoa.
question?
What the hell? So we have 4 particles, and we weigh them individually. We get 20 grams each. So when we weigh them 4 next to each other, they're 80 grams. But when we combine them into a nucleus, they suddenly have a lower mass.
Does it have to do because they're like in a nucleus?
Yeah, we're going to get to that in just a second. But okay, if you're not having a brain ache right now, then you're not paying attention. But the second thing that's going to be even worse, okay, watch this.
Okay,
Now,
okay.
what's the mass of this?
70 grams.
Yeah, we just said it's 70 grams. Now we're going to really hurt your brain. We're going to take the 70-gram nucleus. We're going to take it apart. And now we're going to remeasure.
Oh, I got all that.
We're going to remeasure
Every single part.
those 4 separately. Now that I've taken that nucleus apart, how much do the 4 things weigh separately now?
20 grams.
Each 20
No,
grams,
like
so the total
30.
mass is again 80. So we
Yeah.
had 70 grams of stuff,
Y'all don't.
and then we separated it, and the
Interesting.
mass became bigger. So 80, stick it together. $70. Take it apart. Whoa.
80.
80. Stick it back together.
70.
70. And we can go back and forth between these two things. And in each case, when we put the nucleus together, it loses mass. When we take the nucleus apart, it gains mass.
Oh, but why is that?
Why?
Okay, so
Yeah,
first of
how?
all, I use bigger numbers because it's easier for you to understand, but this is real. What I mean by that is, this is actually what happens. So when we look at the masses of protons and neutrons, and we add up the 4 masses, and we'll do that in just a second, and we compare that with the mass of the helium, this exact effect does happen. So when,
How does that work?
hang on a second, we'll get to that. But 2 protons and 2 neutrons, stick them together, you get a nucleus, lower mass. Take them apart, bigger mass, lower mass, bigger mass, lower mass. You can actually do this. This is not something I made up. This is a real fact of the world.
You know what I think it is?
I don't know. What do you think it is?
Well, doesn't it like change when it's like in a nucleus?
Well, okay.
Yeah.
It has less mass.
Bro, I've
Exactly.
missed Philip's question.
It has less mass.
that's
That's
it.
true.
Is
So-
it because of like the density or something?
Is it because it like needs energy
Or-
to like stick together?
Or like
It
electrons, you
collects
know?
more air.
Okay. Well, this is just the nucleus. You're right. There are also electrons, but the electrons have a very small mass. They don't change this fact, but the electrons are also still involved here. This helium nucleus would normally go with 2 electrons. That doesn't make a difference. So when we make helium out of parts like this, the end mass is lower. Now you might say, oh, well, maybe it's not that much. Maybe it's just a little bit. But you guys actually know a place that does this exact thing, a place that builds helium. What thing do you know that makes helium?
Fusion reactor.
Fusion reaction. Now, we don't have functional fusion reactors, so tell me what device you know that you might have actually seen outside today that does that.
Microwave.
Oh, wow, that's not
What?
good. Why is your
I
microwave
don't know.
outside?
I'm just
That doesn't
guessing.
make any sense. And your microwave does not make helium. Okay.
It's
So-
the sun.
Thank you, Sophie. Okay, so it's the sun, people. The sun makes helium.
Yo.
Oh yeah, and that's like fission. Oh no, wait. So what's the
Fusion.
difference between
That's a
fission and
fusion
fusion?
reaction. Okay, now you better hold on, because the mass of the sun becomes lower because of this process, because it makes helium. You guys want to
Okay.
guess how much it lowers its mass every second?
Like half?
Half.
No, by like 1 gram.
By 10%.
10%, people.
Okay,
You
those
know how
are
much
those
the
are.
sun weighs?
How
It's like
about
multiple
like
tons.
in kilograms or tons or whatever?
10.
10 kilograms. Good.
10
I say
tons.
like
1 ton.
0.01 grams.
All right, you guys are just guessing. I love it. It's about 100,000 tons per second.
Bro.
What?
The mass
Whoa,
of the
close.
sun gets lower
Jeez.
by 100,000 tons every second. While we
Bruh.
talked during this class for the last 25 minutes or half an hour, that's like almost 2,000 seconds, that would be about 200 million tons of mass have disappeared from the sun. And our sun has
Whoa.
been doing this not just for a day or a year, but billions of years.
So
And-
does it just get like smaller
It
and
has to-
smaller?
Oh, so it's
gonna
gonna
be-
like
It
go
does
away
get
and then we're gonna have a
does
black
get
hole.
quite a bit smaller through this process. Now, before you're worried that the sun would disappear in front of our eyes because its mass gets so much smaller, I can reassure you that the mass of the sun is so large that it can continue this process for another 5 billion years, which is approximately how long it will shine, without significantly changing its mass. So
Was it like way bigger when time started?
it
Or,
wasn't
like,
that
It'll
much
be as
bigger.
big as
The reason
Earth.
for that is that the mass of the sun is so big. I'll write it down here for you, just to give you an idea.
Okay.
Hey,
I see.
Google,
the mass
How
of the
much does
sun
weigh?
Dead, dead,
Shut.
dead.
Oh my
Is-
god.
2 times
I
10
believe.
to the 30 kilograms.
Alexa,
Hey Google.
shut up.
How much does the sun weigh?
I just wrote it on the board, you doodle.
Oh,
Idiot.
well,
Why are you
my Google
asking
Home is trying to tell me
Alexa?
that weighs like 2,000 pounds.
Oh, brother. Okay,
Who
so,
is
Hey, Google.
iPad?
Thanks.
so
It's Rafi.
Oh, that's happy.
Legally changed his name to
so we'll write
iPad.
the mass loss over here. Just to remind you guys, so 100,000 tons is 10 to the 8
Change his name
kilograms per
to
second.
Fortnite
You
Mobile.
see this number? So this number
Oh.
looks really, really big, right? But this number is so much bigger that it would take 10 to the 22 seconds for the sun to lose half its mass. Now, 10 to the 22 seconds sounds like a pretty big number, but a billion years is only 10 to the 16 seconds. So even after a billion years, the mass of the sun is not significantly lower. Okay. Okay, so
What?
first thing you need to learn, well, second thing, you need to learn what these numbers mean. Second thing you need to learn is that the mass of those nuclei, the nucleons combined, is different from the mass of the nucleons separately. Okay? Now, the mass is gone and it's converted into what? What happens with the mass of the sun? The mass becomes lower, but what does
Energy.
Energy. The sun produces energy. So the connecting equation that I'm sure you've all heard before is that the energy that comes
Oh.
out of this process comes
Equals-
from a change in the mass, and it's
Heard that?
multiplied by c
Einstein.
squared. You've seen this before. This is the most famous equation of physics. E equals delta m times c squared. So if there's a mass change, like for example in our sun, then there is an energy that is released from that process. And this number, c, that's the speed of light. And it's very large. We talked about this earlier when we talked about optics and, whoopsie, we actually didn't. That was actually 10th grade, sorry. So I don't know, did we talk about speed of light yet? No, that was 10th grade, sorry.
Yeah.
So speed of light is 3 times 10 to the 8 meters per second, which is 300,000 kilometers per second, a very, very large speed.
Oh yeah, we talked about that.
We did, okay, cool. So that means that if we turn 1 kilogram of mass, for example, into energy, it would be 1 times 3 times 10 to the 8 squared, which would mean that for 1 kilogram, destroyed, right? We're making the mass disappear, right? It would be 1 times 3 times 10 to the 8 squared. Well, that would be 9 times 10 to the 16 joules. So that's how much energy we would get from just turning 1 kilogram of mass into energy. Now, you guys are probably thinking, I have no idea how much that is. Is that correct?
Yeah.
Good.
Isn't that like a lot though?
No kidding.
That was such a scientific term, a lot. Very, very precisely quantified.
Mm-hmm.
Well, see, you know, it's
that's
all
how we roll
relative.
around here. Okay, so why don't we turn this into money? You guys like money?
Yes.
I
Why
love
don't you turn
money.
into
Everybody
love
likes
money.
money. Hello.
I don't
So-
have any money.
Same.
I know. So as I always reinforce with my children as well, I'm sure your parents are very quick to point out that you guys are freeloaders and just living off them, right? So you don't actually pay
Damn.
for energy, but your parents pay for energy. So they pay for energy in a variety of forms, right? And so how do they pay for energy?
With money.
Oh,
Kilo.
You ain't nothing but a broke
Stunden.
boy.
they
I
do
think
pay
they
for it
pay
with
with
money, but what kind of, how do they buy energy?
Bei Kilowattstunden.
Kilowattstunden. So they
Companies.
buy kilowattstunden for electricity. Okay.
Mhm.
Wow.
Yeah. They buy gasoline for the car or diesel for the car. They buy gas for your heater, maybe, or oil for your heater, depending on how your house is or apartment's heated. But let's talk about electricity specifically. Okay. So they purchase it via a process of a kilowatt
Mein Name ist Basil.
hour. Okay.
What if they have solar panels?
Okay, that's cool. That works too. You can use a solar panel to produce power as well, but let's assume a kilowatt hour is the purchase is what you've got because you don't have solar panels. We'll just assume that.
Okay.
So a kilowatt hour, what's a kilo?
1,000.
1,000.
Yeah,
Good.
that's
Very
what I was gonna say.
1,000. And what's a watt?
1 billion.
Oh, we never learned that.
Okay.
Isn't that like either joules per second
It
or
is a
like
joule per second. Very good. So you should have learned that in 8th grade, and I will not check with your 8th grade. It wasn't me, was it? I hope not. Okay. All right. So 8th grade physics teacher should have taught you that. So that's a watt is a joule per second. And how many seconds are in an hour?
60.
A
Oh, I
lot.
love when people say
In an
that.
hour.
Oh,
Bro,
wait,
you tripping.
wait, that's 60
Boring.
times 60, 360. I don't know.
I think it's 3,600.
3,600.
Exactly.
Exactly. So, okay. So we have here a kilowatt hour, which is 3.6 million, right?
Mm-hmm.
Whoa.
Okay. So we have this, if you turn 1 kilogram into nothingness, into energy, you get 9 times 10 to the 16 joules. Well, 1 kilowatt hour is 3.6 times 10. Whoopsie, I missed the 6 here. So times 10 to the 6 joules. Well, that means that if you turn
Wait,
1
is it
kilogram,
3.6?
3.6.
For the 3.6, okay.
Yep, there we go. So that means we can find how many kilowatt hours this is. 1 kilogram destroyed, right, is how many kilowatt hours of energy? Let's figure it out right here. So this number divided by this number is how much? You can use your calculator or your phone to calculate that. I'll do the same thing.
I
Broke boy.
Is that 3.6?
It is 3.6 times 10 to the 6. That's correct.
yeah.
So how many kilowatt hours does that produce? What do we get? What do you guys got?
I'm confused.
Syntax error.
Okay, so this is the amount of energy that is produced by 1 kilogram of mass being destroyed. Just 1 kilogram. Like a liter of milk
Okay.
or a liter of orange juice. That's about a kilogram. If you turn that into energy, you would get out 9 times 10 to the 16 joules. Got it? And
Yeah.
we figured out that your parents purchase energy in the form of kilowatt hours from the power company. And that's how much 1 kilowatt hour is in joules. So we can find out how many kilowatt hours this kilogram of mass destruction produces by taking the energy that's produced in destroying that kilogram of mass, and dividing by how much energy 1 kilowatt hour is. So this number here divided by this number will give you the number of kilowatt hours that are produced when 1 kilogram is destroyed.
What
Okay.
are those numbers?
The top number is the energy produced by destroying 1 kilogram of mass, 9 times 10 to the 16 joules. So remember, the sun destroys 100,000 tons of material every second, right? So just one of those kilograms, right, that the sun destroys, that's how much energy is released. This number is how much energy is in joules in 1 kilowatt hour, which is the unit of energy your parents pay for when they're purchasing energy from the power company. So this divided by this tells you how many kilowatt hours this 1 kilogram of destruction of mass produces. This divided by this. Did somebody type it in?
I think it's 2.5 times 10 to the power of 22.
That's Yine, that's not quite correct. 2.5 is right. But I think you typed something in wrong because it should be 2.5 times 10 to the 10, right? 16 divided by 16 on top, 6 on the bottom. So maybe you had a minus sign here or something like that. I'm not sure. But it should be 2.5 times 10 to the 10 kilowatt hours. Okay?
Mm-hmm.
Okay, or 25 billion kilowatt hours. Now you might be
Is
like
that
interested.
more than we use in a lifetime?
That's a really big number. It's way more than we use in a lifetime. Do you guys know how much your parents pay for your Strom?
Yeah, 39.5 cents.
Good. Let's
Bruh.
use 40 cents to make the math easier. So this is 2.5 times 10 to the 10. Let's multiply that by 0.40 euros because that's how much 1 kilowatt hour costs. That's pretty accurate. Okay?
Okay.
Okay.
Would that mean the energy would be like dead cheap?
What's 0.4 times 2.5?
0.1.
Rafi's returning.
Just one. It's just one.
Oh, what?
Just one.
Why though?
Spitzname oder Real, sag ich dir nur.
Huh? Why is it just one?
0.4 times 2.5 is 1.
Oh wait, yeah, never mind.
Digga, Zoom Mobile ist so ranzig.
Yeah.
So,
Mobile.
Oh, that's a lot.
How much money you got? A lot.
That's a lot of damage.
so
Young
if
thug
you
out
were
there.
able to go to your, well, you'd kill
No
everybody in
kidding.
Berlin. But let's just pretend for a second you could go to your fridge, take out a liter of orange juice, and somehow turn that into energy through
Bei uns gibt's
this
nicht mal
process we
Liter Wasser.
described, and then somehow get the money paid to you that the electrical company would charge for that much energy, you would get 10 billion euros. That's
For
how
just
much
like
that
for 1
energy is worth.
kilogram of mass.
If you were able to destroy 1 kilogram of mass, you would gain 10 billion euros. That is a very
Was?
But
large.
wouldn't that like cause like massive?
So this is a very big number. Okay. So I mean, you're like,
Okay.
oh, Bill Gates is rich, Jeff Bezos is rich, whatever. But
They still
even-
can't pay help.
if you wanted to get this conversion, hey Ben,
I'm out here turning orange
Wait,
juice.
how much money
I'm out
does
here
the
turning
richest
orange juice
person on
into
Earth
energy.
have?
I'm the richest man on earth.
There we go. You get the
Mr.
idea.
Glassman, I have a question.
Yes.
If we're getting rid of so much energy, or at least of some energy, how come that if we break the atom apart, we have a larger mass? Because isn't that like energy lost then?
You are correct. So actually in this process, well, hang on a second. So
Gavin.
coming back to this idea. So in this
Mein
process,
Name ist Basil.
hey, okay, Rafa, shh.
Sorry.
Okay. So when we take two protons and 2 neutrons and we combine them together,
Wouldn't that make deuterium?
it is not deuterium. Deuterium is just this. Deuterium is hydrogen 2. So you can take 2 deuteriums and combine them into helium 4. That works.
Oh,
In
okay.
this
And then
process
tritium
of
is
making helium 4, mass is lost and energy is released. When we reverse the process, if we take this helium and we break it apart, that would require energy. You've done
Can we
this.
like write that down as like a,
Yes,
a
I will.
sentence?
Yep. I
Thank
will.
you.
See, the stupid part about Zoom, you never really see the board.
Yeah, you do.
What do
Well,
you
Go in
mean?
the
not when you talk.
Galerie-Ansicht. Go in the
You know?
I'm not
Galerie-Ansicht.
sure. That's a setting problem. So I think you're okay. So I got another board for you guys, so we can write that down. So we can write this down.
Rechts Kamera.
Combine. Oh, I misspelled combining. That's bad. Combining 2p and 2 neutrons into helium-4 releases energy. Now, you guys have a name for that you learned in chemistry. A reaction that releases energy is also called.
Exothermic.
Good job. That's an exothermic
Sam.
action. Okay, but you can also obviously reverse this, breaking helium-4 into 2p and 2 neutrons. Absorbs or takes energy. Okay, so it takes energy to do that, and that process therefore has what name? You guys learned this in chemistry as well? Endothermic. Very good.
Crazy.
Good. So we have a general understanding, at least. Those are the ideas. The lecture I did today is pretty tough to understand, so you want to work through this again. I'll post this on YouTube, and you'll have access to it. Otherwise, we need to arrange another time for next week because we have no class on Friday. It's a holiday.
Oh.
So,
Yeah, it's like the 75th anniversary of World War II,
well, that's
right?
the following week, but we're going to have to find a different time. Okay. So I'll because I don't want to miss meeting with you guys. I think that would be bad because we have 2 holidays in a row, May 1st and May 8th. So that would wipe us out 2 weeks in a row. So I'd like to find another time. Maybe the following Monday at lunch or something would work. But I'll figure out a time and I'll be in touch over Classroom and let you guys know.
Okay.
Okay?
Wait,
right.
I have one more question.
Yes?
Why does it wait, so how does it release energy to
Good.
combine them?
Yeah. Well, so far we've just described it. We will next look at what's actually going on more in detail. This is not it. We're going to stick with nuclear physics for the rest of the semester. Okay? So we'll learn more about it, and this was just the intro. Okay?
Mr. Blessman?
Yep.
Doesn't like NASA spend like millions of dollars like researching this?
This is hugely researched in Germany and America. There's actually a huge. I gotta kind of actually have power running out, so I gotta go. But yes, there's a lot of research on it. Okay, I'm gonna end the meeting because I'm out of power.
It's probably
That's why your shoes raggedy.
Bye, Mr.
Bye-bye.
Blackman.
Thank you.
Mein Name ist